Alright, so what we're going to do is we're going to go over solubility equilibrium, which is KSP. We've gone over equilibrium for acids and bases. We've gone over equilibrium for like acids and bases, Ka, Kb. We've gone over for gases, which is Kc. Now we're going to do the last one, which is KSP. KSP involves a solubility product constant, which is dealing with ionic compounds that are insoluble. So if you look, here's an example of a chart you could find in a book. If you notice right here, the KSP values are listed for a bunch of different species. All these things, if you use solubility rules, you would classify these as being insoluble compounds. So the first step that we need to be able to do is write out what's called a solubility equation. The equation is what we use to actually put together our solubility expression. So you take a compound like CaF2. Whatever the compound is, the solid precipitate is going to go on the left-hand side, because what we're dealing with is we're dealing with compounds that are slightly soluble. So calcium fluoride is going to go on the left right here that I have in the box, and it's going to break up into its ions, although we know it's insoluble, so we're going to really say this is slightly soluble. So when this breaks up, the subscript for Ca is 1. It breaks up into 1 Ca2+, and the subscript for F, or fluorine, is 2. Breaks up into 2F minus. So the insoluble compound ends up on the left. You break it up into the ions, or slightly soluble ions. I end up with Ca2 plus 2F minus. So really what you do is you're looking at the subscripts determine the number of atoms on the right-hand side. When we go to write a KSP expression, it's the same that we've done. It goes products. If you notice up here, here are the products over reactants. The one thing is we do not include the reactants in any KSP expression because what we're dealing with is something that's a solid. And if you remember back to the previous chapter, solids and liquids are not included in the equilibrium expression, so our KSP expression ends up looking like that on the bottom, right there. KSP is equal to bracket Ca2 to the first power, Ca2 plus to the first power, F minus to the second power. Alright, so if we look right here, let's do another sample. For example, barium carbonate. If I'm going to write out the equation for barium carbonate, I'm going to write barium carbonate on the left-hand side, which is BaCO3. That is going to be a solid. I'm going to break barium carbonate up into its ions. Bam! Ba2 plus CO3 2 minus. 1-to-1 ratio. If you notice, the subscript here technically is 1, and carbonate is a polyatomic ion. There's only one of them listed. Then I go to do my KSP expression. I would say KSP is equal to the concentration of Ba2 plus to the first power and CO3 2 minus to the first power. There's my KSP expression. I do not include barium carbonate, the solid, in the expression, and that's how you write it out. Here's a couple other examples. If you look at lead iodide, if you look right here, it starts out as PbIO3 2. So when you break it up into one lead, which is Pb2 plus, and two iodates, which is IO3 3 minus 1. When you go to put in an equilibrium expression, the 2 for the number of ions becomes an exponent in the expression. The insoluble compound goes on the left. The ions it breaks up into goes on the right. You put it into expression. You never have a bottom on any of these expressions. So one of the key things in order to do this is you're going to have to go back through and make sure you know your solubility rules. That's muy importante. That's Spanish for very important. So if we look right here, one of the calculations we're going to have to be able to do is determining KSP. So when we talk about the constant, the solubility constant KSP, this is what a typical problem will look like. It'll mention the fact that you have to calculate KSP, and it will give you a compound. It gives us calcium fluoride. So when you go, the first thing you do is you start with the reaction. CaF2, you break it up into Ca2 plus, 2F minus. Your KSP expression, you will end up with that right there. Ca to the first, F minus to the second. The next thing they ask you to do is when you have to calculate molar solubility. We're going to call that S. So what they will do in the problem is give you a way of finding molarity. Remember in the other chapters we've learned molarity is moles over liters. If you look right there, they tell us we have that many grams in 10 milliliters of water. So all we're going to do is convert whatever they give us into our problem into S. That will be our molar solubility. One of the things we need to be aware of is we're going to do like a mini ice table when we do this, which is going to look like this. You're basically going to take CaF2 double arrow Ca2 plus 2F minus. When you go to break this up into an ice table, a mice table, mini ice, your initial values are going to be 0. This is going to be plus S. This is going to be plus 2S, corresponding just like we did in the previous chapters with whatever the coefficients are. Equilibrium values are going to be S and 2S, right? Same kind of thing we've been doing in the previous chapters. When we go to find our values for molarity, what we're going to do is we take the 10 milliliters, that's going to go on the molarity equation on the bottom, so I'm going to put 0.010 liters, changing 10 milliliters into liters. And then I have to take the 1.5 times 10 to the negative 4th grams of the compound and change it to moles. So I'm going to go over here. I'm going to write 1.5 times 10 to the negative 4th, and that's grams. So how do I change it into moles? I divide by the molar mass. The molar mass of this is 77.8 grams. When I divide those two in, I get 1.93 times 10 to the negative 6th moles. So I'm going to take that over here, put it on top. All I'm doing is calculating molarity. 1.93 times 10 to the negative 6th over 0.010 liters. I end up with a molarity, or my S value is going to be 1.93 times 10 to the negative 4th. That's my S. Then what I'm going to do to solve for my KSP is I go to my E line. This value is going to represent my S here. This value, the S goes in here, and I get my values for the ions, whatever the ion concentrations are at equilibrium. So since this is just S, I'm going to say this is the same thing as just saying 1.93 times 10 to the negative 4th. In order to get this value for F minus, because there's two of them, I have to actually double that value. So I'm going to double that value, and I end up with, when I double that, 1.93 10 to the negative 4th times 2, I end up with 3.86 times 10 to the negative 4th. So my equilibrium value is 3.86 times 10 to the negative 4th right here. This is the same since it's just S, 1.93 times 10 to the negative 4th. Last thing I have to do to find my KSP is I'm just going to take these values and pop it into my expression. This is going to go in here for F minus. That's going to go in there for Ca. Those are the concentration of the ions. I basically square the value for F minus, which is 3.86 times 10 to the negative 4th. And I take the value 1.93 times 10 to the negative 4th here for Ca, multiply that times F, whatever F minus is squared, and I calculate my KSP value. That's all you have to be able to do to calculate KSP. Is you first will find a molarity. They will give you grams. They will give you a volume. Change it to molarity. We've done that in previous chapters. Make a little mini ice table so you understand the relationship between calcium and fluorine. Plug the values back in the expression, and you get a calculated KSP value. Pretty easy. It's simple. All right? That's it.